Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogba Jr., your math tutor and instructor of mathematics at the University of Liberia. In my today's lesson, I'll be looking at differential equations, and particularly under differential equations, I'll be looking at variable separable method and type 2 of variable separable method. So type 2 provides that when you have a differential equations and you cannot apply the variable separable at the first look of the problem, then you can see as to whether you can reduce it to variable separable method. So that's step 2 of variable separable method. So let's see how we can solve additional problems on our. We solved initial problems before, so you can check our videos and see how best you you learn, you practice well. Please don't forget to subscribe if you have not subscribed. Like the video, share the video with your colleagues and friends everywhere. So let's get started. We have question number 28, and question number 28 is on a variable separable. So variable separable, we have solved up to 27 problems. This is the 28th problem. So we have x plus y plus 1 raised to the second power dy by dx equals to 1. So if you look at this problem, no matter how you expand this thing and fight to separate the variables, like putting x on one side and putting y on one side, you are not going to go anywhere. So we remember the chain rule in differentiation methods, like the way you will go for the innermost portion and allow that portion to be some other variable, unknown variables. So this is the same thing here. We know that x is an independent variable. Y is the name of the function. It's a dependent variable. When x is differentiated, you get 1. But when y is differentiated, you attach dy by dx because it's the name of the function. So based upon that, we can allow our u to be this so that when we differentiate, x will leave the problem. Then we'll only be left with y. So we can say let u equals to x plus y plus 1. So du by dx. So we're differentiating u respect to the independent variable x. So this is just 1 plus dy by dx. The next thing we need to do is to solve for dy by dx, because we have already substituted this with u, so we need to solve for this. So to solve for this is to just, make it the subject of the equation. Minus 1 equals to dy by dx. So you have solved for dy by dx. So you put it in now. So this whole thing is just u raised to the second power. This dy by dx is du all over dx minus 1 equals to 1. So now we can simplify the problem. So u times, so it's u square du over dx, and then u square times 1 is just u square equals to 1. So we'll multiply all sides by dx. We'll have u square du minus u square dx equals dx. So we have u square du equals, we send these ones on the other side of the equation. So it becomes u squared dx plus dx. So the x, we can factor the x. So if the x is factored out, you have it like this. So in this first case, this first term now, you have u squared plus, and then yeah, we just have 1, such that the x times this is u squared dx, and the x times 1 is dx. So what do? We have x here, so we don't need this expression, so we divide it on both sides. U squared plus 1. So we have u squared du, u squared plus 1 equals, so this and this cancel, you just have dx. So now we can integrate both sides now since the variables have been separated. Now we can use u substitution, let's say long division here, and bring in partial fraction, but we don't need to do that. We can use the shortcut method. So we can rewrite the numerator as u squared. Now, down here is plus 1. So u squared plus 1 minus 1 all over u squared plus 1 du. And then equals to some x. So u squared plus 1 all over u squared plus 1 du minus the integral of 1 all over u squared plus 1 du equals to x. So this is just 1, the integral of 1, and the integral of 1 is just u. So this now is 1 over a, and our a now is just 1, that is tangent inverse. So a is just 1, tangent inverse of u all over 1, so it's just u equals to x. So this is u now minus tangent inverse of u equals to x. So what we can do, we can send this, we can bring the value for u. U is equals to x plus y plus 1, and then minus tangent inverse of u, which is now x plus y plus 1, right? So we will have this now to be equal to x. So this x can cancel this x. So we can just have y plus 1, and then we have tangent inverse going on that side of the equation. So in order to get rid of this tangent inverse, we can take tangent on both sides. So we say tangent of y plus 1, and then tangent inverse of x plus y plus 1. So this is just tangent of y plus 1. So this is plus some arbitrary constant c, we did not include it, in fact. So we have some c. So if that c, we can just send the c on the left hand side of the equation and just maintain only the tangent of that on the side. So we can have c on this side. So we have tangent of this is y plus 1 minus c equals to tangent inverse of x plus y plus 1. So this now can just be minus c equals to x plus y plus 1. So this is our general solution of the differential equation. Using reducible to variable separable method. So thanks ever so much for watching. See you in our next lecture. Thank you.